Before I start with the presenting today's speakers, I would like to just advertise an event that we are having at LIFD this on 23rd of June, and it's on a Wednesday from 2 to 3 p.m. And there will be a talk on atmospheric convection, and especially on the Paracon program given by Alison Sterling from the Met Office. So if you're interested, please go ahead and register online. And I think Steve will put the link in the chat. So we hope to see you all there. Okay, I just give an introduction to our first speaker, who is Jane Bay, who is currently a postdoctoral fellow in the School of Engineering and Applied Sciences at Harvard University. She received her PhD in computational mathematical engineering from Stanford in 2018, and she will be joining Caltech as an assistant professor in aerospace engineering from September this year. Her main research focuses on computational fluid mechanics, in particular on modeling and control of wall-bounded turbulence using reduced order modeling. So over to you, Jane.
Thank you. Thank you for the introduction, and thank you for the opportunity to speak here. So today I'll be talking about nonlinear interactions of the self-sustaining process in the near wall region of wall-bounded turbulence, and I'll kind of break up that complex title as I talk. I'd like to acknowledge my collaborators who made this work possible, Adrian Lozano-Duran from MIT and Beverly McKeon from Caltech. And I would also like to acknowledge the funding through the ERC via the Madrid Summer Program where this work was conceived. So I'll start my talk. Oops. So wall-bounded turbulence is quite ubiquitous in engineering applications like airfoils, wind farms, and atmospheric flows, geoplanetary flows, and so on. And what we now know is that close to the wall in wall-bounded turbulence, the flow is organized. It's not as chaotic. It is chaotic due to turbulence, but is still organized and somehow coherent. So here's one picture that was taken in an experiment by Klein et al. That was published in 1967. And this is an experiment with hydrogen bubbles that were released very close to the wall in a turbulent flow. And as you can see, these hydrogen bubbles, if there were no coherent motions, would just convect downstream at random. But you can see that they form these elongated streaks that are aligned in the streamwise direction. So here the flow is going from the top to the bottom. And what they observed is that these streaks will be aligned in the streamwise direction and then start to meander and break down in kind of a bursting event and then reform into streaks. And since this picture was taken, a lot of people have focused on studying this kind of cycle in this near wall region. And it has been named the self-sustaining process of near wall turbulence. So the consensus now is that the streaks, they break down through instability and become X-dependent flow. So these are kind of that meandering motions that were captured in the experiments. And then that X-dependent flow through nonlinear interactions will become streamwise rules. And then the streamwise rules through linear advection refeed into streaks. So this is the self-sustaining process of the near wall turbulence, or SSP for short, and it has been studied by many, many people. One of the pioneering researchers that made the study of self-sustaining process possible is the experiment that I'm showing here. So this is a numerical experiment. It's a kind of an idealized situation where the domain of the numerical experiment, so this is a channel flow where you have two walls that are parallel on the top and bottom. I'm showing just the bottom wall. And the domain of the simulation is constricted such that you only have one streamwise infinitely long streak that is survivable in this domain. So if you shrink this domain any further, the streak cannot self-sustain anymore. So this experiment is called the minimal flow unit. And this had this has simplified that problem of looking at the cycle of the streaks, the self-sustaining process, quite significantly, so that we can study the single streak. Also, this experiment showed that the self-sustaining process of the near wall streaks, they are quite independent from the outer region because of the way the experiment is done. So we'll be making use of this this numerical experiment for this study. And in particular, I'm interested in looking at the nonlinear interactions that connect the x-dependent flow and the streamwise rules in the self-sustaining process. So to do that, I'm gonna start with the governing equations. So here are the incompressible Navier-Stokes equations, and I've already decomposed it into the mean and the fluctuation component. So the mean here is the time and homogeneous direction, averaged in time and homogeneous directions. So this is a function of only the wall normal direction for our channel flow. And I've also moved the nonlinear term to the right-hand side of the equation, and all the other terms to the left-hand side of the equation. So starting with this set of equations, what I do here is then Fourier transform this in homogeneous directions and time. So basically, we're taking the fluctuation that is a function of all the three spatial dimensions and time, and transforming them into the Fourier space, where now it's a function of kx and kz. They're the streamwise and the spanwise wave numbers, omega, that is the frequency, and then the wall normal direction. Another thing is I'm gonna now define f as my nonlinear term here. And once we've done that, the equations one-to-one become these bottom equations that I have here. And as you can see, the left-hand side of the equation is linear with respect to u tilde. And so you can actually combine all of these terms into a linear operator, move them to the other hand side. And by doing that, you get this equation here. So you have u tilde, that is your state vector, being connected to your nonlinear term through a linear operator that's a function of your mean velocity profile. So this will become important later. So another way to look at this linear operator. So this linear operator actually has a name. It's called the Resolvent operator. And you can think of it as an operator where the nonlinear terms are an input to this linear operator, and it outputs the state vector. And this particular process can be decoupled for each of your wave number triplets, the kx, kz, and omega. You can obviously recouple all of them through the connection between the state vector and the nonlinear term, but it's also important to look at kind of what this linear operator does in a mode-by-mode basis. So in a method that was used in McKeon and Sharma 2010 paper, basically we're going to look at this resolvent operator by taking the singular value decomposition of it. And by doing that, you get the left and right singular vectors that we call the response modes and the forcing modes respectively. And they are connected by the singular values that we call the gain. And a simple way to think of it is that the forcing modes are a orthogonal basis for your nonlinear terms. So whatever your nonlinear terms might be, you can do a linear decomposition into the forcing modes. So you can express it as a linear sum of the forcing modes, and those modes get amplified through the gain and then turn into the response modes through the linear operator. Furthermore, if you order them such that your sigma 1 is the largest singular value, you can identify which of these modes get amplified the most. So for example, phi1 will identify the most amplified nonlinear term, and C1 will identify the most amplified response term. And that way you can figure out what are the components of the nonlinear term that will be amplified or suppressed, for example. So here's one example. So we're gonna use the minimal channel at RETAL 180. That's the video that you saw earlier. And we're gonna focus on the wave number that is given by 010. And this signifies the structures that are infinitely long in the streamwise direction and once periodic in the spanwise direction. So this in the minimal flow unit is the most important wave number component. So if we look at the leading or the principal forcing mode and the principal response mode for this case, you get something like this. So I'm gonna first focus on the principal forcing mode. So the principal forcing mode, as you can see, this is a spanwise wall normal cut of a minimal channel. The color in the background signifies the streamwise velocity magnitude. And then the arrows are the wall normal and the spanwise component. And what you see here is that there's almost no contribution from the streamwise component, and most of it is these rollers that form through the vertical and the spanwise motions, and these are what we call the spanwise vortices, or the spanwise streamwise vortices or streamwise rolls. On the other hand, if you look at the principal response mode, you can see that the wall normal and the spanwise components are almost zero, and the predominant thing that you can see is the streamwise component. So this is the magnitude. So technically, this is one is positive and one is negative, and they alternate. But you can see that these are actually what we call streamwise streaks. So going back to our diagram about the self-sustaining process, just by looking at the principal response mode and the principal forcing mode of this minimal channel flow, we can see that the streaks are identified through the principal force response mode. And then the nonlinear interaction that leads to the streamwise rolls can be identified using the principal forcing mode. So the idea here is that to understand how important this principal forcing mode is for the self-sustaining process, we can do an experiment where basically we project out the contribution from this phi1 and see how the self-sustaining process is changed. So whether we're able to cut the cycle and remove turbulence or not will tell us whether this principal forcing mode is important in the self-sustaining process or not. So to do that, we're gonna set up a numerical simulation. Again, this is the minimal flow unit at RETAL 180. I'm gonna use a staggered second order finite difference in space and a third order Runge-Kutta time integration for my simulation. And one key important factor is that when the mean velocity profile is first computed through a DNS, and I'm gonna fix that mean velocity profile as I run my simulation now. And the reason for that is, as we talked before, the resolvent operator depends on the mean velocity profile. So if we compute the resolvent modes, it has to be based on a particular mean velocity profile. So we want to make sure that that part is fixed. So that's where we're gonna freeze the mean velocity profile and just work with the fluctuations, just to make sure that we're not, the results aren't changing because we're changing the mean velocity profile. So then at each time step, what I'm gonna do is in the DNS, when we compute the nonlinear term, from that nonlinear term, I'm gonna project out the contribution from phi1. So this is done at each time step to make sure that we don't have any contributions towards the principal forcing mode. So just to show you the result of what we get, so this is the turbulent kinetic energy as a function of time. So we start here, and then as you progress in time, the default channel is the one where we fix the mean velocity profile, but do not project out the principal forcing mode. And as you can see, this is very typical of a turbulent flow. So you have these kind of wildly oscillating peaks that are seen here. Whereas if we actually project out the phi1, you can see immediately that the TKE decays quite a bit, and it stays close to 0. So it doesn't go to 0 completely, but it stays very close to 0. And you can see how different the two flows are. So this was at y plus of 15. If we actually time average the full results for the entire channel domain, this is what we get. So these are the u, v, and w RMS velocities. And you can see that in the bottom of the channel where we project out the principal forcing mode, you get a significant decrease in the turbulence intensities, basically. And to make sure that this wasn't just because we were removing some energy from the simulation, we actually repeated this experiment using the second forcing mode and the third forcing mode rather than the principal one. And we can see that if we remove the phi 2 instead of phi 1, we do get some reduction in turbulent intensities, but not quite as much. And by the time we get to phi 3, not much has changed. So it kind of is very similar to the default channel case. And it's worth noting that the energy that we're removing in all of these cases are very similar. So phi 1, phi 2, and phi 3, in terms of the energy contained in the nonlinear parts, they're similar, but their effects are significantly different. So kind of the conclusion that we can get from this is that the principal forcing mode that we've identified is a quite important nonlinear interaction in terms of the self-sustaining process. So then my next question is, how do we figure out where the nonlinear interactions come from? So what are the x-dependent flow that leads to this nonlinear interaction in particular? And to do that, we can go back to our nonlinear term, the definition of it. And so if we take this nonlinear term and look at the 0, 1 component, we can write it as a convolution because this is in the Fourier space and this is a nonlinear term. And we can rewrite as a sum over all the wave numbers in the streamwise and the spanwise direction. So we have this convolution sum, and for each of this interior terms in the summation, we can look at how much it contributes towards forming phi 1. And we can do that by computing the projection onto phi 1. So we can give that a name. So we're going to call that contribution alpha. And basically alpha determines the contribution of wave number nm and minus n and 1 minus m to forming this principal forcing mode. So by doing this, we can identify what are the important interactions, modal interactions that form phi 1. So if we plot the average value of alpha as a function of the streamwise and the spanwise wave numbers, we can see that only a few of these tiles are significant. And in particular, these 4 tiles that identify 2 pairs of interactions, they account for more than half of the generation of phi 1. So these are the most important nonlinear interactions of the x-dependent flow that contribute towards phi 1. So like I said, there are 2 pairs, and each pair is actually a mirror image of each other. And because the x wave number, the streamwise wave number is non-zero, this indeed identifies the x-dependent flow in this diagram. Because they're mirror images of each other, we're just going to choose one randomly and study that. And the idea is that we're going to look at the simulation and extract instances where contributions towards phi 1 from these nonlinear interaction is large. So the math behind it I'm going to skip, but you can refer to the paper if you're interested in exactly how this is done. So we look at the instances where the contributions towards phi 1 is large. We're going to call that strong nonlinear interactions. And we're going to conditionally average the modes -1, 0 and 1, 1 in this case to see what coherent structures we can extract from that. So if we do that, so here are the conditionally averaged strong nonlinear interactions. So on the top, we have the streamwise, wall normal, and spanwise component of u hat minus 1, 0. And on the bottom, we have the same for the 1, 1 mode. So it might be a bit difficult to discern, but basically on the top, what we have is a streamwise motion that is alternating between high speed and low speed. And in between those two, we have a vertical motion that is going up and down. So if we connect these four arrows, you get kind of this round motion, which signify spanwise rules. So these two components, you can look at them and you can see that they make up spanwise rules. And then on top of that, you have motions in the spanwise directions that are basically shearing these spanwise rules. So if we kind of draw a cartoon of that, it's going to look something like this, where you have these round motions that are being repeated, obviously, and then they're being sheared in the spanwise direction. The bottom one is a bit more easier to discern. So you have these oblique waves that are moving in kind of in a diagonal direction, forward and backwards. And also they're also moving up and down based on their direction. So a cartoon would look something like this, where you have fast moving motions and then slow moving motions that are alternating in a 45-degree angle-ish. And then you have up and down motions that are associated with it. So we're going to call that oblique streaks. We can also repeat that experiment, not by doing conditional averaging, but looking at the correlations for the same instances. So we look at the autocorrelation of the velocity components, and when we do that, we can see that so these are contributions from all the wave numbers, but still we can see that they resemble what we obtained from conditionally averaging particular wave numbers. So the streamwise velocity component looks similar to what we said was oblique streaks. And then this motion here from the wall normal and the spanwise component look quite similar to what we've seen in the spanwise rules. So to recap, basically, we've identified the principal forcing mode as an important nonlinear interaction. And looking back and going to x-dependent flow, we can see that the interaction between these oblique streaks and the spanwise rules are what create these the principal forcing mode, and thus the nonlinear interactions. So to conclude, basically, we've used resolvent analysis as a tool to study the nonlinear interactions of the self-sustaining process of wall-bounded flows. We've shown that removing the principal resolvent forcing mode suppresses turbulence quite significantly, and that only a few wave number pairs are responsible for the generation of the principal forcing mode in this nonlinear interaction in particular. So we've used conditional averages and also correlations to look at the coherent structures that are responsible for that nonlinear interactions. And it turns out that the spanwise rules and oblique streaks, they interact to produce the principal forcing mode. So that's kind of what I have talked about today. If you're interested, you can take a look at the paper that has been published in the GKB Centenary edition for JFM. And with that, I'll take any questions you might have.
Thank you, Jane, for the nice, interesting talk. I will go to the chat to see if there are any questions. Rich, how are the spanwise rules and oblique streaks related to any linear instabilities of the streak?
Yeah, so that's an interesting question. So when the streaks start breaking down, you actually have a lot of contributions from many different wave numbers. So the breakdown of the streak is not a linear process. It's actually due to nonlinearity. And so it's difficult to say where those components are coming from, but they do definitely exist in the flow. And that's what is feeding into the nonlinear interactions.
Another question from Rama: how would these findings change if the Reynolds number were much higher?
Yes, so because of the time constraint, I didn't have much time to talk about the higher Reynolds number case that is discussed in the paper. But what we see is that when we look at higher Reynolds numbers, there are obviously a lot more wave numbers that are associated with that nonlinear process. So we can repeat something very similar for higher Reynolds numbers, and it'll have a impact on the level of turbulence. So it'll suppress turbulence, but not at the level you see here. So for example, if I go back to this plot where we see almost a complete suppression of TKE, in the case of a higher Reynolds number, they will still be significantly lower than these black lines, but they'll still kind of exhibit a similar peaky structure. So instead of being just flat.
Your important modes correspond to those in the Weyler, or other
yeah.
models? Yeah.
Yeah, so I would say so. So it has been studied, you know, before, and they've used different kind of approaches to study it. But basically, yes, the nonlinear interactions, the wave numbers that we've studied are the ones that have been highlighted by Wallach and others previously. I guess the most significant difference is that here we use these orthogonal bases to study particularly what within those wave numbers are important, rather than just the wave number itself.
Could you comment on how this merges with the analysis on linear processes that Adrian presented a couple of weeks ago? I don't know if it's...
Yeah, so I guess maybe going back to this diagram. So as you see here, I've been talking mostly about this nonlinear interactions and what are kind of the precursor structures that lead to those nonlinear interactions. I would say the talk by Adrian mostly looked at instabilities here, where he looked at, you know, how the streak breaks down and feeds into this x-dependent flow. So it's part of the same picture. I guess the focus is slightly shifted.
If you take the mean flow as given, if you took all the nonlinear interactions that you think are important, how close would you be getting a model that reproduces a self-consistent mean flow?
I'm not sure if I quite understand the problem, the question, but basically, I would say the equation for the mean is separate from the fluctuating equations. So when you look at the equations, you can look at the mean equation and then the fluctuating equation. So right now, all the study that I've done is focused on the equation for the fluctuations. I would say to reproduce the mean, you would still need, you know, all the interactions. There are definitely studies out there that look at this, but I can't really elaborate at this moment. So yeah, maybe if you have a question, just email me and I'll get back to you after the talk.